My name is Chao. I'm from Inna University, South Korea. Today I will present this topic. And first of all, let me summarize our research. The purpose is we want to solve the problems of standard genetic algorithm and the problems of hybrid genetic algorithms. And by the way, we want to improve the performance of parameter estimations. And the research method I used in the paper is benchmark problem study, algorithm comparison, and simulation study. The potential applications include parameter estimation and optimization design. And in the presentation, there are 4 parts, and today I will focus on the 6th part. In our lives, torque sensors are very important to measure the torque of crank, rotor, shaft, and something like this. And they play a very important role in automobile and some electrical applications. In torque sensor family, where passive wireless torque sensor are attain a lot of attention because of their small package size, no battery needed, and their non-working range property. This figure will give you some information about the passive wireless torque sensor. First, the radio unit will send out some signal to read the information from the sensor. Initially, there's no change. Initially the response signal has the same frequency, has the same nature, frequency, and phase. When tension and compression occurs, the substrate of the sensor will be influenced. As a result, the response signal will be changed. By processing the response signal, we can get the torque to be measured. But to achieve this, parameter estimation is needed. There are a lot of parameter estimation methods. In most publications, Fourier transform is used, but it has some limitations. And maximum likelihood estimation, least square estimation, they will spend much time to get the estimation frequency. Hilbert transform are used to estimate the damping, so it's not very suitable to estimate the frequency. As an alternative, neural network, particle swarm optimization, and differential evolution and the genetic algorithm are used in some applications because of no major need of prior information about the problem. Genetic algorithms are used widely. The genetic algorithm can be divided into 2 parts: the standard genetic algorithm and the hybrid genetic algorithms. For the first one, usually it uses best fitness-based selection, single point or 2-point crossover, and constant mutation property. As a result, poor local search ability and premature convergence will become a problem. To combine different techniques with genetic algorithm, we can integrate all the advantages into one and get better performance. But we need to trade off the global and local search ability. And for hybrid genetic algorithm, its design is complicated and it has some inherited problems. To solve this, we are focused on how to improve the performance of genetic algorithm rather than to integrate more techniques into one. And in our work, we are focused on these three parts: how to improve the population diversity, and how to enhance the information exchange, and at the last, how to improve the searching ability. In the following time, I will describe this in detail. To improve the population diversity, we first divided the individuals into two based on their fitness values. The individuals with high fitness value will be divided into the benign group, and instead of discarding the poor individuals, we just reserve them in the malignant group. In every iteration, their fitness value will be recalculated, and they will migrate to another group or stay in its original ones based on their new fitness values. And for many genetic algorithms, single point crossover is used. By using this kind of crossover, a random crossover point is generated, and then the substrains behind the cut point will be exchanged with each other and generate two new offspring. From this figure, we can see that the substrains from the cut point are not exchanged. So, in some degree, the information exchange is not enough. To solve this problem, we propose a two-step crossover. The individuals are divided into n substrains based on the number of estimation variables of the problem. A probability PC1 is used to select the substrains. After that, the selected substrains are used to implement crossover, and finally, after these two steps, we can get a new population. And in many genetic algorithms and hybrid genetic algorithms, the mutation probability is set as a constant all the time. As a result, the evolution will fall into local optimal rapidly. To solve this problem, we noticed that at the first beginning, a small mutation probability is good for quick convergence, and as iteration goes on, the number of similar individuals will increase rapidly, and at the end, stability and convergence are very important. So based on this analysis, we propose this adaptive mutation. Finally, we can get this curve. The flowchart of the proposed genetic algorithm are listed here. First, an individual population is randomly generated. After that, the fitness values of individuals are calculated. After that, prejudice-free selection and two-step crossover and the adaptive mutation is carried out. But after these 3 steps, a new population can be obtained. A new best individuals can be obtained after this, and the determination condition will be tested. If it finishes, so it will go to end. Otherwise, it will go on this iteration. To verify the performance of our proposed genetic algorithm, benchmark problem studies are first used. These problems are widely used in the algorithm for optimization. To compare the performance of our proposed genetic algorithm, standard genetic algorithm and particle swarm optimization are used, and table 2 lists the parameter configuration for them. And the simulation results are listed here. From these figures, we can see that the results of our proposed genetic algorithm are the best. And at the end of iteration, we can see that the evolution of standard genetic algorithm or PSO are almost stopped. However, our proposed genetic algorithm shows strong ability. If more iterations are given, it is predicted that it can achieve better performance. Instead of implementing experiment, we use simulation study. And this one are the we use this equation to present the response signal, and these 2 equations are set as the processed signal, and to estimate the signal, we use this objective function, and the parameters and the values for the parameters are set like this. Similar to the benchmark problem study, we use this parameter configuration for different algorithms, and we get this result. From the first figure, it is observed that some part of the curve of our proposed genetic algorithm are disappear. That's because its estimation value is equal to the set 1. And from other figures, we can see that the performance of our proposed genetic algorithm are better than others. So based on our research, we get this conclusion. The shortcomings of standard genetic algorithm and hybrid genetic techniques were summarized. A novel genetic algorithm featured with a prejudice-free selection strategy, 2-step crossover, and an adaptive mutation mechanism was proposed. Benchmark problem and simulation study were carried out, and comparative study of different algorithms were implemented. Results showed the priority of proposed algorithm, and in the future we will do some experiment for this proposed genetic algorithm. And this is the references. Thank you.